Hi everyone, I'm Anneliese. I'm a first year PhD student with Professors Alejandro Lopez Valdez and Shrija Shankar. Bear with me if my throat is a little croaky, it's been a bit bad the past day. But my PhD is focused on how we can achieve accessible brain health monitoring through wearable devices. And in this study, I looked at classifying neurodegenerative diseases using temporal EEG electrodes machine learning. And the results I'm sharing today are preliminary results from an ongoing study that I'm working on. So currently, 55 million people have dementia, with this number projected to increase. Neurodegenerative diseases like dementia are not curable, but we can implement lifestyle interventions to delay or prevent onset. But as we age, it's difficult for us to know how healthy our brains are. The tools that we have for monitoring brain health, like MRIs, CT scans, they're not accessible, and we can't use that to regularly track our brain health as we age. So how can we enable regular monitoring of brain health to allow for early detection of neurodegenerative diseases? So this is full scalp EEG. It's a traditional method that we use for monitoring brain health, looking at the electrical activity of our brains. But a cap like this with 19 electrodes is not something that we can use day to day for monitoring. The applications that we have scalp EEG used for include sleep monitoring, epileptic seizure detection, and dementia classification. But now work has been done to bring us from scalp EEG to ear EEG, and this is an unobtrusive method for recording EEG using only a small number of electrodes placed in the outer ear. And what's more, it can be embedded into wearable devices such as headphones. And the uses that we've already seen ear EEG explored for are sleep monitoring, epileptic seizure detection, and brain-computer interface, but not yet dementia. However, we have seen two examples in literature which took temporal electrodes from a full scalp EEG and looked at dementia classification on this. So the first example achieved 98% accuracy for binary AD classification against healthy. And the second example achieved 88% accuracy for MCI classification. MCI is a precursor for Alzheimer's characterized by memory loss. So this shows that binary classification can be achieved using temporal electrode data. But as we know, dementia is an umbrella term used to describe multiple different types of neurodegenerative diseases. One of this is Alzheimer's, others include Huntington's. So being able to have a binary classification of a specific type of dementia against healthy control isn't going to be good enough. We need models that can handle a continuum of dementia types. So this leads us to our research question for this study. Can temporal EEG electrode data be used for dementia classification with a multi-class approach? So the data set I used for this study is actually publicly available, and it consists of recordings from 88 people with Alzheimer's disease, frontotemporal dementia, that's another type of dementia, and healthy controls. The readings were taken with a 19 electrode full scalp EEG device. And so from this, I isolated the temporal electrodes, and then I performed pre-processing as shown. And when we're looking at brain health signals, we divide the brain signals into different frequency bands. So slower subbands would be your delta theta waves. And then we look as well at higher frequency bands, like the alpha, theta, and the gamma waves. So we then subtracted the electrode pair values, so corresponding electrodes from the left and right hemisphere, and calculated a lateralized power value. Oops. And then we extracted power-based features, so that included the ratios between the fast and slow band powers. And we also looked at a 1/f spectral slope metric, and this looks at the power distribution across all the different subbands from delta to gamma. And so results. Our binary classification achieved the best performance of 81% using a light gradient boosting model. I have a confusion matrix above me, and you can see the proportion of classifications on this. The diagonal that I've indicated in orange is the proportion of correct classifications. So we can see that 88% of our healthy controls were correctly classified as healthy control, and 77% of our Alzheimer's patients were correctly classified as Alzheimer's. Our binary classification for FTD versus healthy control also performed similarly well with 81% accuracy. However, looking at our models for differentiating types of dementia, they didn't perform as well. We got 65% accuracy for binary classification of Alzheimer's versus FTD using a k-nearest neighbors model. And then our multi-class classification example with all healthy controls, Alzheimer's and FTD, achieved 63% accuracy. And so the confusion matrix I have above me is the multi-class example. If you look at it, we can see that our healthy controls in our Alzheimer's patients actually performed pretty considerably well. And we struggled with classifying our FTD patients. It was kind of like a mix between they were misclassified as healthy control, Alzheimer's as well. So what this suggests is that we need further feature engineering to be able to improve these models. I've pulled an example from literature that used the same data set as us. However, they pulled their features, they used complexity features and used full scale electrode data. They achieved better accuracy than us for the binary Alzheimer's versus healthy control. But we performed similarly well for the binary FTD versus healthy control. But we did do a lot worse for the differentiating different dementia types. So what this could suggest is that isolating the temporal electrodes caused some loss of information, or it could be that to be able to differentiate between the dementia types, the power-based features that we use just weren't enough to differentiate them, and maybe complexity features are needed here. So to summarize, we used temporal asymmetric power electrode data to build multi-class and binary dementia classification models. Our binary classification performed considerably well compared with literature. However, our models for differentiating dementia types still need further work to be able to achieve the same performance. And so next steps with this work, I'm now looking at improving our feature selection and feature importance so we can understand how the models are making the classifications so we can fix them. And I'm also looking at model robustness. So if we feed in a data set from other dementia studies or other neurological diseases, that our models are going to be robust to them. After this, I'm going to be developing a metric for brain health that we can track through wearable devices. One that's used is the brain age gap, which is the gap between a predicted age and your actual chronological brain age. And then finally, my goal with this is to enable regular monitoring of our brain health so that we can put interventions in place for ourselves to prevent us getting dementia later on in life. So I'd like to say thank you to everyone who helped with this work, and thank you for listening.